We have seen that the ILS indications are displayed in a very easy-to-read format on the CDI. One needle represents the center of the runway, and the other represents the glide slope. When both needles meet in the middle, this is an accurate approach. Deflection of the needles from the center tells you either to fly left or right, or fly up or down. If the localizer needle is to the left side of center, the runway is to your left, so you must fly left to it. If the needle is to the right, fly right. If the glide slope needle is below the center line, the glide slope is below you. Fly down. If the needle is above the center line, the glide slope is above you. Fly up. If the aircraft has an HSI, or horizontal situation indicator, the ILS indications will be included in it, but the glide slope dots and needle may be shown outside the dial, on the side. The HSI allows the pilot to see his chosen heading and the course to the ILS, which is especially useful when intersecting the localizer. Here, we see that the aircraft is heading north to intercept the 030 localizer. As the needle is centered, the aircraft is now on the localizer and needs to turn onto 030. It is possible to use the back beam signals, where the localizer is designed to radiate this information. There are two applications for this. One is to continue to receive azimuth guidance on the missed approach. In this case, the left-right guidance is in the normal sense, and the CDI or HSI needle should be followed as normal. The other is to receive a non-precision approach to the reciprocal runway where a localizer is not installed at both ends. This procedure is not approved in the UK, but examples are still found in the US and Canada. On these approaches, the CDI indications are reversed. Needle left means fly right. On the HSI, however, the reciprocal course can be set, which means that the command indications are correct. So, needle left means fly left. ILS is used to provide guidance down to the pilot's decision height. If at the decision height the pilot does not have the specified visual references required to continue the approach and landing visually, missed approach action must be initiated. The decision height depends in part on the ICAO performance category of the ground installation. There are three categories: Cat 1, Cat 2 and Cat 3, which is subdivided into 3A, 3B and 3C, which provide increasing accuracy and a lower decision height and associated RVR. You must learn these specifications. Not only must the ground equipment be appropriate, but also the aircraft equipment, aerodrome procedures, and flight crew qualification. The ILS is subject to the usual limitations on radio transmissions, which affect the indications. These are beam bends, caused by buildings and terrain, scalloping, caused by ground and atmospheric conditions, and beam noise, generated by the transmitter or interference. Snow and heavy rain can also attenuate signals. Interference by FM broadcasts in frequencies just below 108 MHz has largely been resolved, as all aircraft radio equipment has had to be FM immune for a number of years. In order to protect the ILS signals from interference, critical areas are established around the antennae, where vehicles and aircraft are excluded. Sensitive areas are also established beyond the critical areas, where movement is controlled during poor weather operations. Holding points before takeoff may also be positioned further away from antennae during poor weather operations. Questions to determine a rate of descent, or ROD, or to determine height at a given distance, are frequently asked in the ATPL exam. The answers are all based on the 1 in 60 rule, which states that an angle of 1 degree will, after 60 nautical miles, subtend a side of 1 nautical mile. Let's remind ourselves of these rules, which we studied in general navigation. Let's start by considering height for a given range on a glide slope. Firstly, we need a diagram in side elevation rather than plan view. We are coming down the glide slope, we have a height above touchdown, and we have a ground range to the touchdown. Ranges are given in nautical miles, whereas height is given in feet. If we approximate a nautical mile to 6,000 feet instead of 6,080, this carries out the conversion for us and fits in neatly with the 1 in 60 rule. The conversion is within about 1%, which is close enough for 1 in 60 applications. Angle Z represents the angle of the required glide slope. Using the 1 in 60 rule, if Z is 1 degree, when the range is 60 feet, the height is 1 foot. Multiplying through by 10, 600 feet range will give 10 feet of height. Multiplying again, at 1 mile range on a 1 degree slope, the height should be 100 feet. From now on, we will use the term mile to mean nautical mile for brevity. Statute miles are rarely used in aviation. Most glide slopes are set at 3 degrees, or some angle close to it. So, if 1 degree gives 100 feet at 1 mile, 3 degrees will give 300 feet at the same range. We have now come up with the first of our basic rules. A 3-degree glide slope is 300 feet per nautical mile. A 4-degree glide slope is 400 feet per mile, and so on. The required rate of descent is 100 feet per degree per nautical mile. Now try some practical examples. What should your height be on a 3-degree glide slope at 4 miles from touchdown? (1,200 feet). Now another. What should your height be on a 5.5-degree glide slope at 3 miles from touchdown? 1,650 feet. Now let's calculate the required rate of descent on a 3-degree glide slope for a given ground speed. If we were in a PA-28 or a Cessna 150 or similar, our airspeed on the approach would be about 70 knots. Assume a slight headwind. After all, that's why you select one particular runway over another. And a typical light aircraft ground speed is 60 knots on the approach. 60 knots is 1 mile a minute. So when we are 1 mile from touchdown, we are 1 minute from touchdown. On a 3-degree glide slope, what height do we need to be when we're 1 mile from touchdown? (300 feet). So, we have 1 minute to touchdown and we're at 300 feet. We need a rate of descent of 300 feet per minute. Now assume that we've graduated from training and we're in a regional jet. The approach airspeed is 130 knots, and again we've got 10 knots down the runway. Our approach ground speed is now 120 knots. What range will we be at 1 minute to touchdown? 2 miles. So with a 3-degree glide slope, what height do we need to be? 600 feet. Therefore, with 1 minute to go to touchdown, we need a rate of descent of 600 feet per minute. At 60 knots ground speed, the required rate of descent was 300 feet per minute. At 120 knots, the required rate of descent is 600 feet per minute. This gives us our second basic rule. For a 3-degree glide slope, the required rate of descent in feet per minute is 5 times the ground speed in knots. What if the glide slope angle is not 3 degrees? How will this affect the required rate of descent? The easiest way of dealing with this is to work it out for 3 degrees and then factor it for the required glide slope angle. For example, what rate of descent do you need to maintain a 4-degree glide slope at a ground speed of 100 knots? For a 3-degree glide slope, it would be 5 times 100, 500 feet per minute. So, for a 4-degree glide slope, it would be 500 times 4 over 3, which is 667 feet per minute. Call it 670 for practical purposes. Sometimes you need to calculate the change of rate of descent associated with a change of speed on the glide slope. The rule is simple enough. If you decrease ground speed, decrease the rate of descent. If you increase ground speed, increase the rate of descent. However, it can be confusing if the change is given in terms of headwind. An increase in headwind is a decrease in ground speed. So if the headwind increases, you need to decrease the rate of descent. The rule is, for 3-degree glide slopes only, that the required change of rate of descent in feet per minute is 5 times the change of ground speed in knots. So, if we are on an ILS approach into London Heathrow, which has a 3-degree glide slope, and the speed drops from 140 to 120 knots, what change in the rate of descent must be made in order to maintain the glide slope? The ground speed has reduced by 20 knots, so the rate of descent must be reduced by 5 times 20, which is 100 feet per minute. Now, one for you. You are approaching London City Airport, which has a 5.5-degree glide slope, and the headwind increases by 10 knots. What adjustment do you need to make to your rate of descent? If the headwind increases by 10 knots, the ground speed has reduced by 10 knots. 5 times 10 would be a 50 feet per minute reduction for a 3-degree glide slope. However, we have a 5.5-degree glide slope, so we have to multiply by 5.5 and divide by 3. This gives a required rate of descent reduction of about 90 feet per minute. The information required to be able to fly an ILS approach is contained in an approach plate for the airport. Here is an approach plate for Oxford's ILS DME NDB for runway 19. It is possible to make a straight-in approach from the north, but coming from the south requires a procedure turn, which is slightly more difficult. As we look at the procedure turn, we need to define some terms, starting with the arrival segment. This refers to that part of the flight from the last airway reporting point to the initial approach fix, labelled IAF on the chart. If the aircraft is not coming from an airway, then it is that phase of flight approaching the initial approach fix. The initial approach fix, labelled IAF on the chart, marks the start of the procedure. Unless the IAF is approached from within 30 degrees either side of the centre line, the aircraft would first have to go into the hold pattern and could not adopt the no delay approach. If the approach involves a procedure turn, as on the Oxford plate, the initial approach fix will be an NDB, as in Oxford, or a VOR. Here we see that the aircraft must be at 3,500 feet above the IAF. The procedure in Oxford requires the aircraft to fly outbound from the NDB on a track of either 001 degrees for a light aircraft or 354 degrees for a jet, to a distance of 6.5 nautical miles. This phase of the flight is called the initial approach segment. It also requires a descent to not below 1,800 feet on the QNH or 1,542 feet on the QFE, as we see in brackets. Notice that at this height the aircraft is below the glide slope and will therefore be able to intercept it from below. From 6.5 miles out, the aircraft has to turn to intercept the inbound 194-degree radial, which is the final approach track. The intercept should normally be at 45 degrees, which means that the aircraft will be on a track of 149 degrees. 194 degrees minus 45 degrees. The aircraft must be established before it starts the glide slope descent at the final approach fix, or FAF, denoted by a Maltese cross at 4.7 miles from the threshold. Up to the FAF is called the intermediate segment. The final phase of the flight, called the final approach segment, is from the final approach fix to the missed approach point, or MAP, which is at a specified height, depending upon the type of approach. By the missed approach point, the pilot should have the necessary visual cues to proceed, such as seeing the threshold lights. If the visual requirements cannot be met at the missed approach point, the aircraft must go around and carry out the missed approach procedure, or divert to an alternate airfield. We can now put these segments together.